I guess we can start. Thanks very much, Suzanne, for organizing the webinar. Thank you very much for attending. Um, Today we're introducing in more details a product we launched last week at Formnext, which is our line of dielectric filament, Zetamix Epsilon, so high permittivity material for 3D printing. I'm going to give a few details about the material itself, about the usage, but first let me briefly introduce the company for those who are not yet familiar with Nanoe. Well, Nanoe, we are a material company. We're developing ceramic materials. We've been developing ceramic material for more than 15 years now. Well, it's an industrial company. We produce these materials in all sorts of forms for industrial production, and not only for 3D printing. We have an R&D center with a team of 10 researchers and engineers who are always working into improving these materials, developing new materials, and this is the team who developed the material we're going to talk about today. Nanoe is 15 years old, but the 3D printing business unit is more recent. We've launched Zetamix in 2018, and this is a line of filament that covers ceramic and metal filaments, usually made for sintering, which is really something different from what we're going to present today. So we provide filaments for printing of ceramics like alumina, zirconia, and silicon carbide, and metals, mainly tool and stainless steel. We provide the filaments. We also provide the full solution. That means complete machine solutions with printers, the binding and sintering equipment, so that our customer can start directly printing these materials. Basically, the way it works is that for this, let's say, traditional line of filament we already have, we offer a three-step process where our customers are printing what we call a green part, which is then needs to be binded and sintered at high temperature to get to a dense ceramic or a metal part. So a few years ago, we started working on a new line of filament that was just disclosed last week, which is a line of filament which works slightly different. These new products, the brand Zetamix Epsilon, is a brand of dielectric filaments for radio frequency applications. There's a lot of words that may be complicated for some of you. What does dielectric means and what do we mean by radio frequency? I'm gonna dive a bit into that. I do apologize for specialists of RF, which will feel this is really very, very redundant, but I know we have also people who are more beginners in radio frequency, so I guess we should detail that a bit. So the first thing is, what do we call a radio frequency? Well, basically, going back to your physics lessons of a few years ago, radio frequencies, it's just one part of the spectrum of electromagnetic waves, which goes from really very low frequencies up to RF, which is what we're going to talk about, microwaves, and then visible light and X-ray and so on. So what we're interested in is working in that field of radio frequencies and microwave, where you will have most of the telecommunication equipment. There's a bit of a zoom in on that place where we are looking at. We are developing materials to print parts for this field, typically radio frequencies, which will be more in the range of, let's say, maybe 300 megahertz to 30 gigahertz. That's where we're playing. One interesting side of it is to see immediately, because it's going to come back later on, that means these are electromagnetic waves with relatively big wavelength, between 1 centimeter and 1 meter. And you'll see that's important. That's why I'm mentioning it. this wavelength is very significant in the applications our customers have. So that's it for RF. You've seen the kind of application we can aim with that. Anything from 4 and 5G, mobile phones, satellite communication, Wi-Fi, etc. That's really very, very large. No, second thing, what's a dielectric material? Some customers get confused because when we talk about printing of antenna components, they are expecting a conductive material, which is not what a dielectric is. It's really the opposite. Dielectric material is an electrical insulator. It doesn't conduct electric current at all, which means that basically, usually in an antenna, you will have a conductive component that emits the electromagnetic wave, and dielectrics will be components that you add on top of this first metallic part. The dielectric material, they're mainly characterized by two properties. The permittivity, which is also called dielectric constant, which is written epsilon, which explains the name of our product, and the dissipation factor, which is usually written from delta. We'll get into more details about what these properties means, but you should really remember these. The main properties are epsilon and loss. To get a bit more into what's a dielectric and how it's going to be used in our case, right? We told you it's not actually going to emit an electromagnetic wave, but it can be used because this is a material that the EM wave can go through, and then the material will slow down the wave. And typically, if you shape it in the shape of a prism or lens or whatever, it can deviate the wave from its initial course. And that's one of the things we're going to look at. One of the ways to understand or to see how permittivity can be used in these applications is to see that the higher the permittivity is, the more efficient will be your prism, and the more the wave will be deviated. Now, if we dive a bit more into what happens into a dielectric material, you have an electromagnetic wave coming in. It's a relatively low loss material, so you won't have any attenuation of the wave, but you will see that the wavelength will change when the electromagnetic wave gets into the material. And the higher will be the epsilon, the more the wave will be impacted. That also means it will also have a slower velocity. It will move at a slower rate in the material that it would do in the air. On the right, you have another example where you would have a higher loss material. And in that case, you see you still have that change in wavelengths, but you also have an attenuation of the signal, which has a lower amplitude after than before. And so really what we were looking for when we developed that material was a material that both have a high permittivity, but which has as little absorption as possible, so as little loss as possible. So this is what we've developed with our new Zetamix Epsilon line, a line of 3 different filaments with different permittivities, ranging from 2.2 to 7.5, with very low loss in the material. That was really the 2 characteristics we needed mainly, and our first customer needed was this: a high permittivity and a low loss. You also need 2 other things in order to be able to use it in most applications. We needed a relatively good temperature resistance and some, let's say, reasonable mechanical properties. This is what we have with these materials. You can see that if you compare it with ABS, which is really the benchmark usually, we'll have a material that has a much better loss factor, and this is very significant. A higher resistance to temperature. So for resistance to temperature, we prefer to measure heat deflection temperature, which is basically resistance of the material under a certain amount of loading. And you'll see that you can go higher, significantly higher with the Zetamix Epsilon line than what you would do with a standard ABS. And the mechanical strengths are, let's say, comparable to ABS. For the moment, we only have these data for the 7.5 version of our filament, but we expect, of course, that the tensile strengths of the other filaments will be probably better. So really what's unique with these materials, and it is something that does not exist on the market at the moment, is the combination of all these properties. High permittivity, low loss, relatively high temperature resistance, and a reasonably good mechanical strength. Finding this set of 4 properties on the market is something you can't find at the moment. We also decided to have 3 different level of permittivities, which may seem strange since I just told you we need high permittivity, but actually it does depend on application. In some case, you may need a low permittivity if you want a material that is almost transparent to the EM wave. You will want a low permittivity, typically if you want to print radome or protection parts for an antenna. And if you want to have more interaction of the material and the electromagnetic wave, you will need a higher permittivity. But depending on applications, having one or the other really might be useful. A few details about how we recommend to use these products. There are some really detailed recommendation on our website. So I'm not going to go into much detail, but just wanted to mention that this is a relatively high temperature material. It prints close to 300 degrees Celsius in temperature, which means you need a heated bed. You ideally need an enclosed printer. You quite often need to have an adhesion promoter to avoid any problems of warping. I would say all the typical problems you will have with high temperature materials. It's also a loaded material. So the way we get to high permittivity is by adding a ceramic loading in the filament, a ceramic filler. And these fillers, when you get to high permittivity, so typically the 7.5, make the filament relatively brittle. So we favor direct drives and ideally spool holders that are on top of the extruder, just like you can see on the picture here, to avoid any breakage of the filament. We recommend the use of hardened nozzles because this material is extremely abrasive. And one important thing is we sell filaments with given numbers of permittivity, but the printed part you will obtain will depend a lot on the printing parameters. That means if you print a part with 7.5, but you have a bit of porosity in your material, well, actually your permittivity will be lower. So that's something very significant. There are some fine-tuning of parameters if you want to really get the high permittivity of the material. And of course, the good thing, if you compare it with our other filaments, is that there is no post-processing required. There's no debinding and sintering. You just print the part and use it immediately as it is without any post-processing. You will see in a few of the use cases we demonstrate that some parts could not be made in ceramic. You could not debind and sinter them because of the size or because of other parameters, and that's one of the reasons why we developed Zetamix Epsilon, to be able to make these parts with a material that doesn't require post-processing. So now, last question before going to actual use cases. I would say an obvious question, which is, why do we actually want to print components for radio frequencies? What's the benefit of doing that? Well, we see 3 different benefits. Probably there are some other ones that we haven't identified yet, but I'm going to go through these 3 main benefits. And the first one is very obvious. It's something we see with every 3D printing application. You may want to produce complex parts with shapes that are not easy to machine. You may want to do small volume production, or maybe even tooling that needs to have these radio frequency properties. And 3D printing is obviously ideal for that. But there's more. There's a few other things that really are specific to RF, and I'm going to talk about these now. The first one is you can use 3D printing to produce what we call metamaterials or metasurfaces. That means parts that are structured below the wavelengths, the operating wavelength, the wavelengths we want to use. So I told you at the beginning about the wavelengths we're using. Usually it's going to be between, let's say, 1 centimeter maybe to 1 meter, which means it's relatively easy to structure the part below that size with 3D printing. And the interest of doing that is that you're going to access to functions that you could not do with a traditional component. Here you have an example from Thales, which is the first customer we had and the company we've developed the material with. It's an example of a lens for radio frequencies, where you see the difference between, let's say, a lens made by traditional manufacturing, where you would just machine the shape of a lens. That's what you have on the left here. And by structuring the material below the wavelengths, by making what we call the metasurface, they manage to have exactly the same function. That means this is a lens. It will act exactly in the same way, in a way that it will concentrate the waves. It is exactly the same function, except it's 3 times lower profile. It's lighter and it's even less expensive and more efficient. So that's really the big interest. You can access to let's say we could call these artificial materials or materials that will have very specific functions for RF. And the third thing is really very simple. You can use 3D printing to tune the permittivity with adaptation in the density. It's not exactly a metamaterial, but there is a bit the same idea, which is to say, well, since we're much below the wavelength, if you print porosities, the material will act as a medium material between air, which has a very low permittivity of 1, of course, and the material you're printing with. So you can really fine-tune the permittivity of your material just by printing with different level of infills. So the law, of course, you need to know exactly how the material will behave. There is a law to calculate how much porosity you need if you want a given permittivity. But typically, if you want to be at 5, you can use a 7.45 and print with 15% porosity, and you will have actually a material that has a permittivity of 5. This can be extremely useful. First, if you want to choose a given permittivity, or if you even want in the same part to have several levels of permittivities. And that's really the 3 main reasons we've identified so far that makes additive manufacturing of dielectric really attractive for our customers. Let's give you now a few examples of applications. The first one is really the first application we developed it with Thales. I told you that Thales was our first customers are actually our development partner for this material. We've been working with Thales for 3 years now on printing these materials and printing that kind of structures. And Thales is particularly interested in printing metasurfaces, which will act either as deflectors or lenses, or a bit of both. Here you have an example of really very low profile steering antenna that allows you to do point-to-point communications, potentially satellite communications, effectively replacing a parabolic antenna by a flat antenna using that kind of metasurfaces. Of course, you can see the interest of having a very low profile for some applications. it really brings a huge advantage compared to what would be used alternatively. Here you have another example, which is, I mean, with the same principle of meta surfaces, but it does something different in terms of function. It's a directive lens, so both a lens and a deflector in the same surface. Again, this is really something you can only get with meta surfaces. If you wanted to do that with traditional components, well, basically you will have two components, one lens and one deflector, one prism, and both of these components would be extremely bulky. And by using meta surfaces, we can achieve the same function with a very small surface. So that's really the first application we started with. You can see that these parts are relatively big. That's one of the reasons why we went to ceramic field filament and not a ceramic material. We are printing at the moment parts between 28 centimeters, and the biggest one, which is on the right, is 46 centimeters wide, and we're working on printing bigger parts with the same kind of patterns. So that was the first application with Thales, and then we started looking for other partners. One of such partners is the LEAT, which is a French laboratory on telecommunication and antennas, which has given us quite a few interesting examples of application for these materials. The first one is here you have a radio frequency lens, which basically works in a bit like a Fresnel lens, except that the way we will concentrate the EM wave is by playing with the permittivity of the material, and we play with the permittivity of the material with the infill, which is something I mentioned previously. So that's really a part that would be, I mean, completely impossible to manufacture in another method, and extremely simple to print with our filaments. Another example here of a reflecting lens. So it's not a lens this time. It's actually a reflector and a lens at the same time. So the electromagnetic wave will come in from the front and then come out from the front also. Even though the material is only a dielectric, because of the structure of the material, the way it is structured below the wavelengths, the wave is actually going to be reflected. Here we use two materials in this print. We've used Zetamix Epsilon 2.2 and 7.5 because you needed strong differences between the permittivity of certain zones. You needed high permittivity and relatively low permittivity. Another example here, so I'm afraid we can't really see what's happening in that part. It really looks very simple. These are dielectric resonators for antenna arrays. Dielectric resonator can be used to confine the electromagnetic waves so that you can have arrays of antennas which are relatively close to each other, and that allows to miniaturize the antenna arrays. But to get, let's say, the maximum efficiency, the LEAT wanted a dielectric resonator with several different level of densities in the same part. So these are really very small parts, but inside the part, you actually have three different infills, and these three different infills give you basically three different permittivities in that resonator. And last example, this is really very, very fresh from the printer, because our customer just started tests a few weeks ago. We started some collaboration with a laboratory from Jiangsu, which is also working on 3D printing of antennas. And here it is a bit more simple, let's say, in the way that this is not a metamaterial or whatever. It's just a dielectric antenna. what we call the dielectric helix antenna. But manufacturing this part in a high permittivity material would not be very easy without 3D printing. So that was really an interesting application for our customers. I'm sure they have more in store, but this is really just the beginning. So that's another example. For the moment, that's all. We've just launched the material, so we're receiving lots of inquiries at the moment about new applications. We're certainly going to keep developing on these and keep posting on examples of application for these materials. So if you want to know more, you can follow us on LinkedIn. And of course, we're extremely interested to hear about what you would be yourself interested in doing with these filaments. So if you have other examples of applications, really feel free to contact us both on LinkedIn or by email. Well, thank you very much for listening to me. I hope I didn't make too much mistakes on the radio frequency side of things, because I must say, Nanoe, we are experts of materials and not experts in RF. So I hope I haven't made any significant mistakes, and I'm open to questions if you have any. So first question on when will 2.85 million filament be available? Hello, Leif. I know we've had a few exchange by email. So this 2.85 filament is not ready yet, mainly for a simple reason, which is that we haven't tested 2.85 on printers. We know that usually a 2.85 millimeter is used for printers that have a Bowden drive, that means indirect drive. And we know out of experience that this is not very favorable with brittle filaments. So it hasn't been tested yet. To give you a precise date, I must say I don't know, but I would say at least a few months before it's available. So if you have access to a printer that's compatible with 1.75, I would recommend to start with that. So indication of loss tangent at higher frequency. I'm afraid we haven't tested that yet. I'm sure there are applications in both direction of higher and lower frequencies. Most of these properties we're sharing, they were measured at 10 gigahertz or very close to 10 gigahertz. We did test a few other frequencies, but always in the range of 1 to 50. I must say I can't remember exactly which point we did. It did seem relatively stable in that range. We will gather more data. So we're still working about that. So another question about the frequency range. I guess that's a logical question because every application will require different frequency range. I must say we haven't tested yet all these. We have tested a few different frequencies, but I must say I wouldn't be able to tell you which ones now. And that's the same for tangent loss. So we are not capable of giving you these data for the moment. That's of course something of interest if you have the capacity to measure on your side and are willing to share this information with us. Maybe it's also something we can discuss about, and we would of course be happy to assist any laboratory who wants to do some tests on the material. So the temperature range this material can operate in. So basically, we have tested between relatively low temperature. I can't remember exactly, but I know that we went in the minus, I would say minus 20 or maybe minus 30, up to, we've tested it up to 80 degrees Celsius. Um, the heat deflection temperature is 110, so you can use it up to 110. But depending on your application, there is still a very little bit of loss in the material. So if you have lots of power coming through, the material may heat a bit. So we usually recommend to have an operating temperature a bit lower because you may have a bit of heat from the signal itself, depending on what you're doing. But it's up to 110. The prices, well, all the prices are on the website. I can't give you precise pricing, but the range is around 300 euro per kilo, knowing that we usually do spools of 500 grams. We could do on demand, but the standard size is 500 grams. The datasheet states that the diameter nozzle of the 3D printer has to be 0.4 or 0.6. Actually, you could go higher, of course. We just mentioned that going below 0.4 is not advised. You can do bigger, of course, but doing smaller is difficult because so in the range of filaments we're offering, we have the 2.2, which is basically a simple thermoplastic filament. And then the other ones are loaded with ceramic filler, and this filler will both increase the viscosity of the filament and also it can clog the nozzle if the nozzle is too small. So we usually don't go below 0.4. Actually, if possible, 0.6 is better. So you mentioned the fact that tensile strength depends on printing directions. You're right, we haven't tested yet. That's completely right. We should. And I think we probably measured the most favorable direction. And we measured it on the worst case scenario in terms of material. The 7.5 is really the most brittle material we have because of the high ceramic loading in the filament. That's an interesting question. A question on the level of UV resistance. Well, it is a very good question. I must say we haven't tested yet. Knowing the material is safe, I would say, knowing the matrix, I would say probably quite good UV resistance, but that would need to be checked. And it might be different on the 2.2 and the other versions because of the ceramic filler, which may have an impact on the UV resistance. So probably quite good, but has to be tested. And the last question, does it support all the 3D printers? Well, probably not. The first thing is we haven't, to be honest, completely tested all printers. For the moment, we only offer the 1.75 millimeter diameter. So that already excludes a few printers that use bigger diameters for the filament. We will probably release 2.85 millimeter at some point, but for the moment, we only have the 1.75. It is likely to work on most printers, but again, the filament is quite brittle, so there may be some specific setup to put in place or some small adaptation to do on some printers. About the things I mentioned in the presentation, ideally having a direct drive is better, having the spool of filament placed on top of the printer, just like the picture you can see below me, behind me, I mean, might be more favorable. What about outgazing if used in vacuum environment? Well, I must say, Leif, you have some very interesting questions. And I must say, I'm afraid we don't have the answer to that one also. What we know is that usually when we print, we really try to avoid as much as possible porosities. If you manage to have a dense material, it should not outgas in vacuum. But the big question is, how dense do you manage to print? But again, to be perfectly honest, this has not been tested yet. The product is really, really new. And again, we are open to collaboration with laboratories who would be willing to test such properties. Well, if you have any additional questions, do feel free to put them in the Q&A section. I'll still be there for a few more minutes if you have questions, and then we can close that session. So a question about the polymer biomaterial. Well, this is a patented formulation which is not yet public. The patents will be released soon. As long as the patent is not released, we don't communicate precisely on what's inside it. You have some information, it's a basic information in the data sheets that you can find on our website on zetamix.com. So you have some basic information here, but we we don't give the precise formulation yet. All right. Well, thank you very much for attending to this webinar. Of course, you're more than welcome to visit our website, follow our LinkedIn page to learn more about this, and to contact us if you want to start some tests. We do really recommend, if you're starting to test the material, maybe you've already purchased some spools. We had quite a few purchased in the first days of launch. We really do recommend that you should feel free to contact our team to get some help in starting printing. This material being relatively high temperature and very highly filled, it is a technical material to print, so we're here to help and get you started in printing those components. Well, thank you very much, and I hope to see you again in a new webinar soon.